present the changes you need to get to state, and then talk about some of the technical issues that arise. So I was going to apologize for this being a really technical talk, but I think I'm actually going to be fine. So thank you. Yeah. Okay. So so you can imagine typing being on some sort of spectrum, where on the one hand you have sort of the pure Coq and Agda and systems like this, and on the other hand you have people who sort of don't think about a static type discipline in any way. Right. So there are already research programs that let you try to program in more than one part of this spectrum at once. So probably the most well-known one is gradual type. So they're trying to let you work in, at this stage, like sort of simply typed languages, trying to push into Hindley-Milner while integrating with dynamically typed languages. So there's a lot of efforts on this, typed racket, Diamondback Ruby, articulated Python. There's a bunch of stuff here. Manifest contracts sort of just makes a left where gradual types makes a right. So just out of personal taste, that's not the direction on the type spectrum that I'm interested in going. I want to go the other direction on the type spectrum. I want to start with Hindley-Milner, which, after a lot of talk we all agree is the best. And then I just want to get more stuff. Right? I don't want any less stuff. I want more stuff. Okay.
Hybrid typing. Do people sometimes use that?
Yeah. So I'm going to manifest contracts here. I'm using sort of a technical sense we use from our Popple 2010 paper, and I just want to distinguish it from other things. I'm going to go into a little more detail. This is just sort of the lay of them. Yeah, hybrid typing, there's a bunch of people doing stuff in different ways. I just wanted to show where we are. You could put a lot of things on this spectrum.
Right. Whatever the Haskell implementers decided was cool this week. Right?
Sure, yeah, okay. So to get into more of the technical meat, what are contracts? I encourage everyone, like everyone else, to ask questions. Hopefully this will be understandable from the beginning. So I would say contracts are specifications that you write in code, right? So there are all kinds of specification languages people have. People will use different logics. People will use, subsets of their language. I want to say there's any code in your language. This is what makes something a contract, is that it's freely chosen code. And that typically contracts are checked dynamically. So at runtime, we're going to discharge these specifications by running them. Okay? So this isn't sort of a controversial thing. So I think every modern language has some form of contracts. So at first order, assert is a contract. So this is a specification. You believe at some point in your program that the number n is a natural, and you wrote something in code to check that. That's going to, say, raise an error if it fails and you have certain flags set, and it's checked at runtime. So this is a contract, right? I feel like if C has it, it can't be that controversial. So square root, this is maybe more interesting. So preconditions and postconditions. Here, square root has a precondition that says, you shouldn't give square root any negative floating point numbers because it's not going to exactly know what to do for those, right? Okay, so that's another first order contract. And you can go further, right? So square root is a nice example because you can also give a very precise postcondition. So here, the only functions satisfying these pre and post conditions are square root functions, right? And then diverging functions and things like that. But so one point sort of worth referencing here is the dependency. So everyone see that? So here I've referred back to my argument. This is not an uncommon feature in pre and post condition languages, some kind of dependency. The other feature is just the notation I'm using. So I'm going to use subset type notation throughout the talk. Okay, so this is hope, not folk. So what are higher order contracts? So this is, I think, sort of the interesting bit for people in our community. So the idea here is due to Fidler and Felice in 2002, an ICFP paper. Basically, so pre and post conditions are hard to think about at higher order because it's not really clear who's at fault. In a first order setting, it's really clear the precondition is the responsibility of the caller and the post condition is the responsibility of the function. But here, sort of caller and function get blurred, right? That's what happens in higher order languages. So hopefully many of you have seen this before. I think the best way to explain it is through a little bit of role play, if everyone's okay with that. So here we've got this function. I'm going to be the whole function, and you all are going to be this function f. So we're going to each have different jobs to play. You are going to give me a function f on nats, and I'm going to give you back a fixed point of that function. So this is the game. You don't have a lot to do. Don't worry. So worth noting here is that, again, this is a dependent one. Okay. This is your job, and I've forgotten my animations. Okay, so what happens? If at the end of the day you don't get a fixed point, that should be my fault. Right? So I'm the whole function. You gave me your function f in some sort of good faith, and then I violated that good faith by not giving you a fixed point like the contract said I would. So it's my fault. Similarly, if I call your function with a negative number, well, that's not what's in the contract. The contract says that f is going to be an operator on nats. It doesn't say anything about calling it with negative numbers. So that would, again, be my fault. Right? You gave me your function f, you trusted me, and then I violated that trust by calling your function with a negative number. But, and this is the only responsibility you all have, if you return a negative number, that is definitely your fault, and I'm going to blame you. So you may notice that these colors correspond to the colors in the types, and these colors in the types correspond to positive and negative positions. So this is Findler and Felleison's even-odd rule. So it's nice. So you might worry that a higher-order function would have an arbitrary number of parties to blame, but in fact, just like in the first-order case, there are only two people to blame. Okay, so this is sort of the high-level overview of contracts. There are a number of people doing different types of contract disciplines. The distinguishing characteristic of manifest contracts as a discipline is that these sort of subset notation functions and dependent functions here are going to be the language of types. Right, so in other contract disciplines, there's maybe no types at all. Here I want to say, no, this is the type language that I want to program in. There's no difference between these specifications and the types of my language. So there's lots of languages that have types that look like this. Some of them are on that sort of pure end of the spectrum. The distinguishing characteristic also of manifest contracts is that these are all going to be checked dynamically. In particular, these subset types, X is a B such that E is going to be checked at runtime. Okay, so how does that happen? This is sort of the last bit of intro I'm going to do, and then we can talk about things in more detail. The way this is typically done for a manifest contract system is through casts. So a cast is just something that takes something from one type to another type. Right? If all my specifications are types, this is where the checking is going to happen. So the way to read this is, well, we know that E has subtype T1. It reads from left to right, just the way that like a lambda's argument is on the left and the body's argument. You'd be surprised, this is actually a point of contention. So E has type T1, and I want to treat it as type T2. So the type system will just sort of honor that and treat this whole term as having type T2. But if at any point we can observe that E is not acting like a T2, we're going to raise an exception. So we'll call that blame L. That L superscript is just a source code location. Exactly where it comes from doesn't matter. Let's just assume we have some abstract set of locations and leave it at that. Okay, everyone on the same page? We'll look at how casts work, and then we can start talking about how we add state. Okay, so the easy case is casts between array refinements here. I mean to say subset types. So how does that work? So here I have the number 7. I know that 7 is an int such that true, because true is sort of an easy thing to check. But I want to know that 7 is a natural number. And if it's not, I want to blame L. So the semantics of cast, I'm not going to go into the deep detail of the operational semantics, but the semantics of cast say that, well, this should just evaluate to 7 because it passes. Right? And ultimately, you'd like to hand this off to, arithmetic functions or something. So you need to get the value back out. Okay. If, however, I give a negative number, something that doesn't satisfy the right-hand side here, right, it is not safe to treat -1 as a natural number because it isn't a natural number. So I expect to get blame out. So you might notice that we're not doing anything with the left-hand side. We'll deal with that in a minute. That comes up in the higher order case. Two things. One, just as a first approximation, you can think of the semantics of these checks at subset types as just being an if statement. Do you satisfy the predicate on the right? If so, return the value you got. If not, raise blame. This isn't exactly how you do it in the calculus, but it's good enough. And then just sort of think for a moment how a type system might work. That 7 has a type here that's fine on both sides of that arrow. What does our type system look like to have subject reduction? I think there's going to be a quiz. It's just sort of, it's a tricky type system, right? You need to know a lot of things. So what we'll do is we'll give the constants, say, selfified types. So this is due to Wu et al. From I think a 2004-2005 paper. People have done stuff like this, I think maybe even before that, but the term selfified I heard from there first. The idea that the number 7 has the type x is an int such that x equals 7, right? And if we had, say, subtyping, this would imply all types which 7 passes and so on. And then just to be clear, the type of an operation like division would want to specify its sort of safety parts, right? So here, division needs a non-zero second argument. And then just to sort of, yeah, Derek?
Why doesn't it have a dependent type, which is soft?
I could do that. This is sort of the minimum you need for safety.
Yeah.
I'm lazy. I think it's that simple. Okay, so and then just to think more about what this type system might look like, 5 divided by 0 is an ill-typed term. You cannot write that term down in this type system. You can, however, write down a term that casts 0 to this type, and of course that cast will fail, right? It'll never succeed. So a way that I like to think about this language with casts is that what these casts are doing is reifying the checks that actually happen in the implementations of our partial functions in the language anyway, right? This is the check that, what Camel does when you divide an int by another int, right? Here I've just made the checks explicit in this sort of core lambda calculus. Okay, one more little bit of intro and then I can actually talk about the content. Okay, so cast between functions. This is the real insight that Findler and Felice provided. The basic idea is if I have a function f and I know that it's a t1 arrow t2 and I'd like to pretend that it's a u1 arrow u2, there's really nothing I can do right now. Like I can't open up the closure. That's just crazy talk, right? You're not allowed to do that. So what we say is, well, this is a value. We call these kinds of values function proxies because we're going to wait till this sort of cast function gets applied and then we'll check sort of the smaller parts, the domain and the codomain. So the rule is, if you have this function proxy f applied to some value v, right, we're going to totally unwind the cast. We have a contravariant cast in the domain, right, because v is a u1 if we're treating that whole unit as a u1 arrow u2, and then we'll have a covariant cast in the codomain. I, for some reason, realized I didn't include the dependent rule. The dependent rule is actually kind of interesting. It has an asymmetric substitution, kind of irrelevant for our purposes here. But this is just the general way that it works. Cool? Right, so this is all the literature going back to somewhere between 2004 and 2006, I think is the first for this stuff. Okay, cool. So I wanted to add state to this. So conveniently, I don't think Christos is here, but there's already a paper that does this. Right? There's a contract paper, Christos Dibula, Sam Tobin Haxa, and Matthias Felice in 2012 and ESOP have a paper, Complete Monitoring for Behavioral Contracts, I think it's called, and they give us semantics for state. So let's just adapt it to this setting, right? Can't be that big of a deal. So, so extend the types, we'll add references. Cool, that's definitely the easiest part, right? It's not hard. So we need to extend expressions. Is there a question or? People just heckling. All right. Extend expression, so we'll add reference allocation, dereference, and update. And then sort of one of their core ideas was, well, let's extend. We need to extend values to add the notion of location, and you don't have just bare locations. There's two kinds of locations. There's actual locations that get allocated, and then there's wrapped or proxied locations. So this is just like for the function case. It makes sense when you think of state as being higher order itself, right? You can think of state as either these locations or as a pair of a getter and a setter. And well, of course, we're going to have to defer some of the checking. So here, there's the second kind of state are these proxy states that have a pending cast on them. So here again, the inner state gamma is some ref of type T1, but the system's going to try to treat it as a ref of type T2. Okay. So we've extended our grammars. So now we need to extend the operational semantics. Let's do reads first. So the interesting bit is how do you read and write from these extended bits, right? This is the fundamental change we've made. So I try to dereference a proxied reference. It's well, let's just push it in. So we know how to dereference the inner thing. So do that, and then, well, that's going to have some type T1. Just cast it to T2 because we wanted to pretend this whole thing was a T2. Right? Pretty straightforward. Just wrap it covariantly. Okay, so let's extend the semantics for writes. So gamma is the inner type of T1. V is going to be something of type T2. So we're going to need a contravariant cast here. This, again, shouldn't be too surprising because references are ultimately invariant, right? So So of course we need to have the contravariant cast, and ultimately you need to be able to move between both. So this is just a translation. This is like a, if you know both the latent contract literature, the sort of stuff that Dimowitz and then we're working on, and you know the manifest stuff, this is not a hard translation to do. So great, so we have a semantics, and they've proved that it's correct for their criteria for blame correctness, so that's good news. But what is it going to take to get to the level of a type system that has a soundness proof and a set of reasoning principles that do the sort of things we might want to do in these languages? So I've identified sort of 4 core problem areas for adapting this. And I wanted to present them to you, talk a little bit about some solutions I have, or sort of avenues towards solutions, and I would love to get as much feedback as possible on avenues I'm missing or avenues that you think are particularly good. I should add, I'm actually only in town for a day, so if you could get back to me quickly, that would be great. All right. Right, so these are the 4. There are issues with scoping. There are issues with recursion and divergence. There are issues with semantics in really the sense of meaning. Sort of what do these subset types even mean? And then there are, of course, going to be issues with proofs. So I'm just going to go through these in order, and then I'm going to present some of my ideas in order, and that'll be that. Okay, so the first issue is that locations aren't always in scope. So what this means is that sort of in any dependent type system, you leak the details of your implementation in your dependent types, and we're going to do that, but that's going to now get a little bit worse because we can't just use substitution to deal with scoping issues like people do in the pure languages. Let me show you what I mean. So here's a function that is a manifest contract function that uses state, and what it does is it takes in some function f, and it tries to guarantee that f is not used reentrantly. You don't call f while you're already in the dynamic extent of f. So here's how it does it. It's written sort of a system f style notation. So for all types alpha and beta, you give me a function f of type alpha arrow beta. I'm going to allocate a new reference cell called inside. It's going to start out false. And I'm going to return you a new function, sort of a proxied version of f, that can only be called when inside is not true. Right? You can't call this proxied function when the inside is set. So at first you can call it. It's not set to anything. And the moment you call it, the first thing it does is set inside to true. So you can't do any more calls. Then it calls f, and there's some cast you need to get your typing to work out. And then it clears this sort of bit and returns the ultimate result. So does everyone sort of agree that this is a way to guarantee that a function isn't reentrant? I'm stealing this example from Jesse Tove, I should be clear, who has studied in sort of the more latent side this sort of stateful discipline. Okay, so what type does non-reentrant have? What should we write in there? So you can just read it off, right? So for all alpha arrow beta, x is an alpha such that not inside beta. So like what happened there? That's not great. So like the normal thing you can do when you have just a substitution-based semantics is, well, whatever we defined inside it, substitute that in. But you can't do that for reference cells. So this is issue number 1. Okay. Issue number 2 is issues with recursion. So I can imagine wanting to set up invariants that involve more than one variable. So here x and y have a relationship to each other, right? X is never greater than y. But how do you get started here? What do you do? Do I have to always allocate it in a tuple? Do I need some kind of atomic initialization scheme? Or should I instead have some notion of like scope transactions where I can hold off on checking until I've sort of set things up the way that will make sense? Because once you have state, you get all these idioms like backpatching and things like that, and I might want to support that sort of thing. What's the right thing to do here? So that's one problem with recursion. There's another problem with recursion. So this is a slightly complicated and contrived example, but I want to show you sort of an issue. So let's just see what happens when we evaluate this dereference of G at the bottom. So it's going to go through that cast, and that cast is going to go to this cast, and it's going to go to that cast, and then it's going to go to evaluate another dereference of G. Well, that's really problematic. So we already knew that adding state to something like the synthetized lambda calculus takes us from a converging language to a diverging language. But we sort of knew that you weren't going to diverge unless you called a function, right? Now, because of the semantics that we added to dereference, you can diverge because you dereferenced a cell. So that's weird. I'm going to get back to this. Okay. Issues of meaning. Here's a program that initializes a reference cell x. It's an int reference cell. Gives us a new reference cell y that checks it, that's actually a natural. Sets it and dereferences it twice. Okay, a sort of simple program fragment. So what happens when I add this line to the subset type? So sort of the subset type, it's the same subset of values, but it's got an effect. So like, what does that mean? What's going to happen? If I run through again, the first dereference will succeed, but the second one actually blows up. So, I mean, obviously state violates referential transparency, but like, what is the subset type's interpretation supposed to be at sort of a high level? Put more technically, there's been this principle called value inversion, which is basically a way of saying type soundness means what you think it means. If a value has a subset type, then it actually satisfies that type. And that's just not, I mean, that's true here the first time, but not the second. So like, what notion of possible worlds do we need to sort of understand this correctly? So weird. And then finally, I'd actually have the least to say about this. The proofs for these systems have not been what you would call simple or lightweight. And adapting these sorts of things to state are hard, as Derek and Amal are sort of nodding along as I talk about this. So exactly how to move some of these things to this world would be interesting. So because we have terms and types, things get even a little bit worse. In particular, the type conversion relation proofs get quite complicated. And Sushi and I could talk to you about that. But sort of adapting this to the setting of state seems quite challenging. You end up needing to do rather challenging proofs at the beginning before even proving type soundness. Okay, so in the remaining 2 minutes or whatever before questions, I want to talk about ideas for solutions. So one reviewer very helpfully mentioned a Dunfield and Fenning paper that has this idea of contextual typing annotation. So thank you, whoever reviewer one was. That was helpful. The idea here is that to resolve scoping issues, you can give type annotations that give little scopes, like little contexts inside the typing annotation. So I looked this up and it seems pretty good. The problem is that what they're able to ultimately do is get to a self-contained type. And it seems to me that we don't even want a self-contained type. Like, this is the right thing, right? The type here is the correct thing. We just need we need qualifiers. Maybe we need an existential. So the way that I've been thinking about it, I think a promising avenue, and I would love feedback on this, is some notion of scoped effects. Because the existential doesn't quite capture what I want. In fact, every time you call this function, it's a different inside. And so the effect here seems to capture that better. One weird notion is that this effect is also a binder. And I haven't seen systems that do something exactly like this, so this is just my ignorance. I would love sort of pointers or whatever. Okay. While we're on the subject of effects, I think effects are a promising way to look at recursion and questions of meaning. So one way to solve the problem would be to say, what do you mean stateful contracts? There are no effects in these subset types. And that to me is sort of a little too hard line. Kind of like throws the proverbial baby out with the bathwater. But this would at least solve the problem. I think you can go a step further and say, well, fine, maybe each of these has some set of effects xi, and then maybe, the term can have some other set of effects xi prime, but I need an order on them. And this is not the inclusion order you might expect out of effect systems. This is a xi prime is sort of a set of allocated terms in some order on reference cells that are completely separate from these other x's. So there will be no chance for circularity. This would rule out the G prime, the G contract that ended up dereferencing itself in the middle. Something like this. So this is an idea. Another thought I've had, actually due to Greg Morissette, is using information flow control to to resolve issues with circularity. So you can imagine while evaluating one of these contracts to raise the label on the program counter by some artificial symbol or some family of symbols saying, you're now executing a contract and you shouldn't have effects outside of some pre-delimited scope. So I think this is another promising way. There's dynamic or static ways I could enforce it, which seems appealing because we're already in the game of trading off between dynamic and static things. But it doesn't seem to really resolve the scoping issue. So if anyone has other suggestions for what to do about proofs or other places to borrow from, so Aaron Turan's idea about talking about Rust and substructurality seems also possible here in terms of controlling the uses of variables to avoid recursion. Should I use a monadic semantics and try to be more explicit about what is and isn't impure? So there's other dynamic techniques. Avi Shinar's thesis, also with Greg Morissette, uses runs contracts and transactions and then just rolls back the effects. And that certainly is an operational solution, but doesn't cover any of these sort of static type issues, right? This is sort of an untyped system. So these are just the thoughts I have, and I would love any feedback you could give me on that. Thank you.
So because of my semantics, if you're willing to squint hard enough to your little semantics, Daniel Harman in Edinburgh might have some insights about adding effects into your refinements. And maybe also some ideas about recursion.
What was the name? Sorry.
D-A-N-E-L. Harman, A-H-M-A-N.
Thanks.
Because they're code of office.
Okay.
There?
Yeah, can you go back to the example of the state, go back to your slides.
Yeah, here, yeah.
Yeah, so I'm having trouble understanding exactly what kind of meaning you have even at any intuitive level for what you want to do. Because, I mean, what you showed before was if you have some type with a manifest contract, then when you apply that function, you know just based on the type what contract you have to run. But here, if you have some new inside thing or somehow, it's essentially you have no idea what to run. I mean, the code's not going to write all the code of, well, I can't make any sense of it. And you could possibly need to.
I guess that was what Michael's point was, is that it's kind of partially makes sense. So.
Yeah.
Well, maybe my question is more general. Like, can you give a positive example of something with a manifest contract type involving such a state that is useful?
So you mean you don't understand this one, or you think it's not useful?
I don't.
I think there are a number of examples of stateful contracts that are useful in. Cormac has a paper on temporal contracts, and I think a lot of those are interesting. Some of them are this non-reentrant thing, which to me seems like an interesting sort of thing to do. So if you don't think that's interesting, I'm not certain how to approach it with you. But
didn't we give a talk last year about abandoning projection specifically because stateful contracts are super useful? Like here?
Right, as a manifest contract.
So I understand that here's a manifest contract is confusing because, well, how do you check it if you don't have access to this inside reference cell? Yeah, no, I agree. And like this is, like it, if so, I think one outcome of this could be that this is an ultimate failure of manifest contracts and we should abandon this approach, right? That you don't want certain things reflected in the type and that's just the wrong thing to do. Or there's a way to coherently organize these things. So I clearly here have not adequately revealed what inside is or what it does because the user seeing this has no way of knowing when it is safe to call, right? Or how to do the check and so on.
Maybe more than one would be, do you have examples of stateful manifest contracts that are clearly useful?
So I think
the stateful contracts are useful. I buy the manifest contracts are useful. I'm not understanding what is a good example of where stateful non-manifest contracts together sort of make sense. Maybe I just get one other.
So I think the most general answer I can give is, well, I'd like to be able to, in a manifest contract language that has state, I'd like to be able to write any code I want in that predicate in the subset type. So whether that state is merely writing to log files or anything else, I would like to be able to have a coherent semantic account for that. So maybe offline we can go over concrete examples. Ranjit?
I think so. So I have a bunch of feedback. So one is you should look at the stuff that sorry, quick. What's his name? Rooster Lino, and that entire community has been worrying about a lot of things like this because there is a OO world. It's all imperative. You have this kind of partial initialization, and you have various tricks where you want to say, here's a class invariant, but pay no attention to this invariant until I set this bit. At which point, things have actually become useful. The invariant is supposed to hold from now on, right? So you should look at that. The other thing I would say is you mentioned this remark about throwing the baby out with the bathwater if you start doing things like this. I mean, the one message I get from your talk is you don't even want to put the baby into this bathwater. In a sense, it's so complicated that you really want these contracts to be pure. Because another thing I'm worried about is what if evaluating the checks actually changes the behavior of the program other than just saying something bad happened? I mean, fine, you wanted to fail stuff, something bad happened. But I don't want to, by evaluating one of your contracts, actually take a reference and then pause execution, go down some different path. That's yet another terrible thing that might happen. And you want to somehow make sure that the effects are benign and something. And the last thing, since Amal has raised her hand, is that they did all this stuff. I guess I'll let Amal say this. They have this really nice example in HTT, which does exactly this business where you create an existential. I'll let Amal tell you.
Yes, precisely. So what I was going to suggest is that perhaps you should take your re-entry example and try seeing if you can write a type check version in HTT, because vortex theory has a monad for effects, and it really allows you to be precise about when allocation is happening and so on. So that might be something. Another thing in reference to what Ranjit was saying, that, maybe the bathwater thing, if you have effects going on inside these types, then yeah, lots of bad things could happen. At the very least, you would want whatever effects are going on inside the types to be affecting disjoint locations than the ones that your program cares about. I mean, I would think that's most likely, I would think that the examples that you would come up with that are useful would follow that pattern. So you need some way of, imposing some sort of structure and sanity on this so that people get it. Right? And again, HTT is really nice in terms of reasoning about this because you can talk about separation. So that might be a good experiment. And otherwise, I would be nervous.
Okay, fair. No, I appreciate the references. Yeah, that's great. Thanks.